Hello everyone, I'm Christina and welcome to this A-Level Mathematics Calculus Series video. This is video 22 and we are differentiating the functions e to the x and a to the x, and this is part 1. So our objectives for this video are to be comfortable differentiating the exponential function and to go through some worked examples differentiating the exponential functions. So we're first differentiating e to the kx. So for our function y equals e to the kx, where k is a real constant, dy over dx is equal to k lots of e to the kx. So notice that when we differentiate e to the kx, we get e to the kx back. So we get our original y function back with a constant k in front of it coming from the index here. So we will look at other examples where we have a function of x, a function with powers of x in the exponential, but for now we're just looking at when we have a real constant in front of our x in the exponential. And then when we differentiate a to the power of x, we have y equals a to the x. Our dy over dx is going to be equal to ln of a times a to the power of x again. We get our a to the x again when we compute the differential. So this one is slightly different from our e function, and a derivation that we can use to remember this is if we let a equal e ln of a. So you should be comfortable seeing that the left-hand side here is equal to the right-hand side. You can have a look at another video on the natural log and the exponential function, but for now we have to accept that the natural log ln is the inverse of e. So if we raise e to the power of ln of a, we just get a back. Okay, so that's why we can rewrite a as equal to e to the power of ln a. And so if we have y equals a to the x, we can in fact write that as e ln of a to the power of x. Using our laws of indices, we can say that's e to the x ln a. So now what we want to do is differentiate this. So dy over dx is equal to, well, instead of differentiating a to the x directly, we can just differentiate e to the x ln a, because we know the rule for that. So we know that the factor of k in the index is going to come down, and then we're going to get our exponential function out again. So dy over dx is equal to, our k is our ln a, so that's going to come down. And then we just get our exponential function there, so that's e to the x ln a. Now, if you remember our rules for logs, ln a times e, this here is equivalent to ln of a to the power of x, and of course ln is the inverse of e, so then this just becomes ln of a times a to the power of x. So that's a derivation that can help you if you're stuck on how to differentiate y equals a to the x, if you forget that dy over dx is ln a times a to the x. Okay, so now let's just do a really short example. Example 1, if we have f of x equal to 2x squared plus e to the 3x, find f dash of x. So this is our first derivative function. So our first derivative function will come from differentiating each term of f of x. So if we differentiate 2x squared, we'll get 4x. And if we differentiate e to the 3x, we'll get 3e to the 3x. This is our e to the kx where k equals 3. And so if we look back on differentiating our e to the kx, if y equals e to the kx, our dy over dx is k times e to the kx. Our k is 3, so when we differentiate it, we get 3 lots of e to the 3x. And that's exactly what we have here. Okay, so in part 2, we're going to look at some further examples.